Hi, welcome to my project. I'm AlNouri and today I'll be presenting to you Momentum Falling Film Project. So we are given a problem where we have an oil with certain given properties flowing down a falling film of a certain thickness on a vertical wall. We want to find the mass flow rate and the velocity of the liquid. This is in the steady state part. There's also we need to use Phoenix in order to reproduce this flow in the unsteady simulation part of it. So the assumptions that we are taking is that first, the fluid density and viscosity are constant. So that means we can use the Navier-Stokes equation. Second assumption is that we need to neglect the disturbances at the edges, inlet and outlet, because the length and the width are very large in comparison with the film thickness. The non-vanishing velocity found is Vz, and it's not a function of z. It's a function of x, which is the spatial variable. So we only have Vz in the direction of x. The pressure P is a function of x, and it's nearly constant. We also assume that the resulting non-vanishing component of the stress is tau xz or tau zx. For the boundary conditions, we have one boundary condition called the no-slip boundary condition, where at the solid-liquid interface the velocity of the liquid equals the velocity of the solid. The second boundary condition we used is the gas-liquid interface at a constant x. The stress tensors are equal to 0, the other ones, not xc, and this is applicable when the gas side velocity is small. This makes sense because the viscosity of the gases is, of course, much less than the liquids. In order to solve this problem analytically, we first have to remember the equation of motion. If we simplify it, we will obtain the Navier-Stokes equation. And this equation is applicable, like I said, for constant density and viscosity of fluids. So the method to do this is, since we have Vz of x, the only term, all the other velocity terms in these equations found in the appendix B6 from the book are all cancelled out to 0. That leaves the pressure, which is just also a function of x. Gravitational term is also dependent on the direction, like the axis we took before. The next thing we do is we cancel the terms. As you can see on the right, these are the equations after all the unnecessary terms are cancelled. Then we obtain, if we simplify equation B.6.1, we have the pressure becomes a function of the angle and another function which is found to be the atmospheric pressure. So that means the pressure is containing hydrostatic pressure and ambient pressure on the system. The next thing we do is use the continuity equation in order to see if anything is useful from it. So we have this continuity equation in Cartesian coordinates, but as you can see, all of the velocity terms cancel, and Vz is not changing with the z direction like shown here, d by dz. This term will cancel out because it's only changing with the x direction. That leaves the change in density with time which is equal to 0. So that's just like the assumption we had, or the given, that the density is constant. That means the continuity equation is satisfied. The third and last equation, general equation we will use from the book, is Newton's law of viscosity. This one tells us how the stress behaves, and also all of the stress terms are cancelled because it's only in the xz direction, and even the normal stresses terms cancel out because the gradient of v is equal to 0 due to it having a constant density. We are left with this equation. Now I will go through the derivation. So we have the stress equation that we found before. We need to substitute what we found for tau xz in it, and then we will integrate in order to find an equation for tau xz. We have C1 here, so we need to insert the first boundary condition, which says that no shear stress at the surface of the liquid happens. So that means at the gas-liquid interface. That means that there is no shear between the gas and liquid interface. That's because the gas is surrounding the system and it does not create any shear with it. So tau xz equals 0 at x equals 0. And that gives C1 equals to 0. Then we substitute Newton's law of viscosity in the obtained equation above, and we integrate in order to get an expression for Vz, which has C2 now. To find C2, we need to substitute the boundary condition 2, which says no slip, which is the no slip condition. Vz equals 0 at x equals the thickness. C2 is this expression, and then we substitute it in this in the found expression. So after this we can find the value for Vz in brackets, and Vz max will Let's discuss the first part of the results. So according to the analytical solution shown in the top figure, the laminar velocity distribution is parabolic in shape, as shown by this side view. The Reynolds number was found to be 5.1, which meant that rippling is negligible and the flow is laminar. That means that the flow is described by high momentum diffusion and low momentum convection, and that all makes it laminar. For the bottom figure, it was obtained by the Phoenix code, the Navier-Stokes that we ran, and only a few parameters were changed and transformed in the code in order to fit the unsteady behavior of the flow in the Phoenix part. So the bottom figure shows that the flow behavior of the oil in the film is first on the wall in the purple region, then it moves through the green area, which means down the ramp, until it reaches the yellow part, which is the exit. The flow doesn't look much different if you compare both the flow patterns, and the curves are actually not that far from constant, but they have a bit of a curve. And we should note that the values we found for Vz max are exactly the same. The one found from the code is also 0.153, which agrees with the one we found before from the analytical solution. Here we have the second part of the results, which illustrates the thickness versus the velocity. So in the initial small time steps at 0 and 1, unsteady flow can be said to happen because the increase is more prominent in smaller values of the thickness, while at thicker film, steady state can be seen because the graph is constant and the velocity is not changing with the thickness. The thickness is not changing with the velocity. Now for the middle time steps, The increase in velocity is almost always happening with the thickness, even though the steady state can be observed at the maximum velocity Vz 0.0017 meter per second and beyond. The largest time steps ran till 300, and the shape does not change after it reaches the time step of 24. And it is unsteady for most of the curve, only becoming steady state at a thicker part of the film, which you can see in the above graphs at 0.145 meters and higher. So there are three things we can conclude from this project. Falling films are usually explored in evaporation and gas absorption experiments, process coatings, and wetted wall towers. Unsteady flow simulation didn't really give a drastic difference. The reason for this might be that the code of the Navier-Stokes was not transformed drastically, so that means it will give similar results to the steady state flow. Or the film thickness is very small, so it also doesn't have an effect on the state of the flow. The thickness and the time steps and velocity have a proportional relationship according to the graphs I showed before. As time steps increase, velocity is more affected by the change in thickness, which causes the shape of the graph to be less constant and increase at a higher rate. Thank you for listening to my presentation. My references are in the next slide.